Good day. Welcome to Matrix class. Okay, so in this video, we're going to continue talking about the basic of a set. Well, it starts off with something easy. We're just going to say that sets can be finite or they can be infinite. And this is fairly straightforward. Very easy to understand the difference between the two. So, when the number of elements in a set is bound, we say this set is finite. Okay, so let's look at some quick examples of a finite set. Let's see denote the set of the first 7 letters of the alphabet. So C is equal to, we have A, B, C, D, E, F, and G as elements of this set. You can see that this set has exactly 7 elements. And this would be an example of a finite set. I think that's very easy to see. So, as another example of a finite set, let M denote the set of months with the first letter of M, so you kind of go through the months of the year. You have 2 months with the first letter of M, and those months would be March and May, so that would be the elements of this set M. But what's important here is to see that we have exactly 2 elements, and this is an example of, again, a finite set.
So, in infinite set, and I think you can kind of just from the word picture what that is, has an uncountable or infinite number of elements. And let me kind of go on this war here, uncountable. If you think about it really, when you say a finite set has a countable number of elements, what are we saying? Well, we're saying that it's bound, it has some number of elements, right? It doesn't go on forever. So, when we say that it's countable, it might not be countable by human being, but conceptually it's countable. When we think about this infinite set and we say it as an uncountable or an infinite number of elements, you can possibly count it because it goes on forever and ever and ever. You will never have an end to that set. So as an example, let's kind of use this capital letter N to denote the set of natural or counting numbers. In case you don't know what the natural counting numbers are, it's basically the whole number without the number 0. But it's a good example of an infinite set, right? Because if you think about the natural numbers, you start at 1 and you increase in increments of 1. So, you go 1 and 2 and 3 and 4 and 5 and 6 and 7 and 8 and 9 and 10. It keeps going out forever. Then, there is no largest natural number. However big of a natural number you can think of, you can always add 1 to get it a big or a natural number. And that's the point of the 3 dots here. This is called an ellipsis, and it tells us that this pattern continues forever. Okay. It's going to continue forever, so again, after 4, you'd have 5 and 6 and 7 and 8 and 9 and 10, so on and so forth. So, this is an example clearly of an infinite set. It goes on forever and ever and ever without end. Another example, let P to note the set of prime numbers of so P equals, and we start with 2, then we have 3, then 5, and 7 and 11, and again we have our ellipsis to say that the pattern continues indefinitely. So not a very difficult concept, just kind of have to know that a finite set is bound, right? It has some number of elements. But an infinite set is unbound, right? It doesn't have specific number of elements because it continues forever and ever without end.
Okay, so now let's start talking about relationships between sets. So we talk about in the first video the fact that two sets are going to be equal if and only if they contain exactly the same elements. Remember, the order does not matter. So let's suppose we have the following sets. Let me have 4 sets here. So we have a set A. It contains the elements 6, 1, and 3. We have set B contains the elements 2, 1, and 8. We have set C. It contains the elements 1, 8, 2, and 9. And we have set D, which contains the elements 1, 6, and 3. So what exactly can we say about the relationship between the sets A and D? So let's look at A and let's look at D. And what you can see is that, okay, you have a 6 here and here. You have a 1 here and here. You have a 3 here and here. So they have exactly the same elements, but they're not in the same order. What we can say is that set A is equal to set D. And I can flip that around and say set D is equal to set A. It doesn't really matter how I write that. So set A is equal to set D because again, they have exactly the same elements. Now, next question here is, can we state the same thing about the sets B and C? So set B and C, let's look at those B and C. So we have a 2, 1, and 8. Over here, I have 1, 8, 2, and 9. So we can say that D equals C, and the reason for that is because this set C has an element of 9 that B does not have. So because they don't have exactly the same elements, the two sets are not equal. So we can say that B equals C, and the reason for that is because this set C has an element of 9 that B does not have. So because they don't have exactly the same elements, the two sets are not equal. So we would say that C is not equal to B, set C is not equal to set B. Now there are other things that we can go into here. We're going to talk in a minute about subsets. So let's scroll down, we'll talk about that. So when all the elements of a set are also elements of another set, such as, so here we have a set A, which contains the elements 1, 14, 18. And set B, which contains the elements 2, 1, 8, 7, 14, 12, and 18. We can say that set A is a subset of set B. So can you see that you have a 1 here, you have a 1 here. You have a 14 here, you have a 14 here. You have an 18 here, you have an 18 here. Now B is a larger set, but if you look at B, B contains all of the elements of set A, so that what we mean by subset. So again, when all the elements of the set, such as this set A here, are also elements of another set, such as this set B here, we'll say that A is a subset of set B, and this is denoted as set A is a subset of set B. To know more about sets, watch the next video. Thank you for watching.